Good morning. This is Dr. E. Manjoolatha, Assistant Professor of Mathematics, Annamacharya Institute of Technology and Sciences, Tirupati. Today we are going to discuss about the control charts for attributes. In the previous sections, we discussed the control charts for variables. Variables means it's measurable quantitatively. But come to the control charts for attributes, we cannot measure quantitatively. See, that is here the quality characteristics like good or bad, fit or unfit, defective or not defective are some of the attributes in nature. Thus, attributes can be measured and ascertained but cannot be measured quantitatively. Quantitatively means how much. That is, we cannot measure. In control charts for attributes, the sampled units are divided into two categories. One is defective and not defective. So, before going to the defective, see what is mean by defect. Defect in the unit means if a unit does not conform to specific quality standards, does not conform to specific quality standards, it is referred as defect in the unit. Next, come to defective unit. A unit which contains more than the permitted number of defects. So, permit more than the permitted number of defects, then we said that that unit is a defective unit. Okay, these are the differences between defective and defect. Okay, in these control charts for attributes also, we are having three types of charts. One is P chart, that is control chart for fraction defective. Second one is control chart for number of defectives, that is NP chart. Control chart for number of defects per unit, that is third one. First come to fraction defective chart, that is P chart. P chart is designed to control the proportion or percentage, that is 100p, of defectives per sample. So here we are using the word proportion in the P chart. So P chart is used for control chart for fraction defective. Fraction means here we are using the proportion. So in these three charts, first we are going to see this P chart. Come to the P chart. Come to this method for P chart. First step is calculating P bar, that is number of defectives in all the samples combined by total number of items in all the samples. If we go through the problems, we can understand how can we compute P bar easily. Now come to the step 2. Compute the standard error P, that is sigma P. This is the formula for this sigma P, square root of PQ by N. So here Q is equal to 1 minus P. So after computing P, we easily calculate Q. Step 3. Using the formula given below, compute upper control and lower control limits. So these two are the formulas for the controlling limits. One is p plus 3 into square root of p of 1 minus p by n. And instead of plus, you are using minus for the lower control limit. So these are the limits that is in the step 3, upper and lower limits. Okay, come to the step 4. Draw the control line CL at P bar and UCL LCL at the dotted lines. Then plot the individual fraction defectives as points and interpretation of the result. See, these all steps, if when you are doing the problem, these all steps easily we can understand. So now come to the problem. See the first question in the P chart. Samples of 100 tubes are drawn randomly from the output output of process that produces several thousand units daily. Sample items are inspected for quality and defective tubes are rejected. The results of 15 samples are shown below. So, total how many samples they are taken? 8, 9, 10, up to 15. Totally they are taken 15 samples. Next, on the basis of the information given above, prepare a control chart for fraction defective and give conclusion. So clearly they are given fraction defective in the question. So that we are using here P chart. See, totally they are given 15 samples and each sample they are taken how many tubes? 100 tubes. So first sample they are taken 100 tubes and how many defects are there in that 100 tubes? 8 were the defective. And second sample then again they are taking 100 tubes and in that second sample also 10 tubes were defective. So similarly up to 15th sample how many defectives out of 100? 9 were the defectives. So this is the data they are given in this question. Now first calculate the fraction defectives of each sample number of defectives. See control chart for fraction defectives. These are the sample numbers and each sample number of defectives. Now this table column represents the fraction defective, that is 8 defectives out of 100. So 8 by 100 you got like this. Next 10 were defected out of 100, that is the fraction will be 0.10. Like this the last sample 15, in this 15 sample 9 were defective out of 100, so that the fraction defective will be 0.09. So clearly we found the fraction defectives or each number of defectives we can find the fraction defect. Total number of defectives is 169. So see in the first sample 8 defectives, in the second sample 10 defectives, third sample 13 defectives. Like this in the 15 samples we are having how many defectives here? This one plus this one, you got the total number of defectives, that is 169. Okay, what is the fraction defective sum? 1.69. See, sum of the fraction defectives we got, summation of p is equal to 1.69. So from the given data, what we find this from the given data? Fraction defectives. Okay, now using the formulas we can find p bar. The formula is total defectives by number of items inspected. See, total defectives. Just now we have calculated that total defectives is 169 and total items inspected. In the first sample, we are taking 100. Like this, you are taking how many samples? 15 samples. Each sample is 100 tubes. So that we get 15 into 100 in the denominator. So 169 by 15 into 100, how much you got? The value is 0.113, that is the p bar value. Okay. Now 3 sigma control limits for p chart. Control line, that is p bar, we calculated already 0.113, and UCL of p bar, that is p bar plus 3 into square root of p bar of 1 minus p bar by n. So substituting all the values here, you got UCL is 0.208. Similarly, instead of plus, you're writing minus here in the LCL. So substituting all the values, you get 0.018 of LCL p bar. Okay. So now you got p bar, UCL p bar, LCL p bar. Now draw the graph for p chart. See, take the samples in the x-axis. Here these values represents the fraction defective values. So this is the fraction defective values in the y-axis and sample numbers in the x-axis. Okay, and draw the graph for these points. See, this is the first point, 0.008, and this is the second point, this is the third point. Taken points like this, you have to draw the graph. Before going to draw the graph, first draw the CL line. What is CL line? 0.113, and UCL line, is 0.208, and LCL line is 0.018. So after that, plot the sample points for 1, and this is 2, and this is 3 point, and fifth. So like this you have to plot the points. So from this graph, what we observe here, since all the points are lying within the two control limits UCL and LCL, so the process is under statistical control. So all the sample points lies between these LCL and UCL, so that the process is under control. Okay, this is P chart. Now come to the second chart, that is NP chart, or control chart for the number of defectives. See, NP chart shows the number of defective items present in each sample. If the sample size n is constant and the number of defective items found in each sample is d, then d by n is the fraction defective p. So p is equal to, simply you are writing d by n. So here n is a constant, that is a sample size. Okay. In this chart, NP chart is modified version of the P chart. Here we are not using the fractions. In this chart, we can directly plot the number defective items in samples rather than the fraction or percentage of defectives as in the case of P chart. So this is the difference between these two charts. Here the fraction defective, we are not using this word. Okay, directly we plot the number, defective numbers. Here, the formula for the NP chart is 3 sigma control limits for NP chart. Upper control limit is NP bar plus 3 into square root of NPQ, and LCL is NP bar minus 3 into square root of NPQ. Here, this is CL, NP bar. The method for drawing NP chart is similar that of P chart. Now come to the problem. See, the first one is the following data refer to the number of defectives in 10 samples of 100 items each. Construct an appropriate control limits. See, they are given the data like this. P chart is very useful to finding this. So, P chart shall be appropriate control chart for the given data. So, this is under come to P chart. Now, come to the second question. The past records of a factory using quality control methods show that on the average 4 articles produced are defective out of a batch 100. What is the maximum number of defective articles likely to be encountered in the batch of 400 when the production process is in state of control? So clearly they given the production is under control. Okay, so defective out of a batch 100, how many articles? 4 articles were defective. Now you have to find, and you have to find out of 400 the number of defective articles we are going to find. For this, see the solution. P bar or P dash, that is process of fraction defective. Directly you have to use this D by N. D means defectives 4 and N samples 400. So that gives P bar or P dash. So 4 by 400 means 0.04. From this P bar, you have clearly calculated Q bar or Q dash. That is Q dash is equal to 1 minus P bar. That's we know. Substituting that P bar value in this Q dash, you get the value of the Q dash like 0.96. Okay. Here n is equal to sample size 400. So D is the number of defectives in a sample of size n. D is equal to NP and the control limits are this LCL of NP, UCL of NP. So using these formulas, you can get after the calculation, you can get the upper control line or upper control limit is 27.7. So nearly it is 28. LCL is 4.24. So in the production process in a state of control, then the number of defective article D likely to be encountered in the batch of 400 must must be between the control limits 4 and 27.7. Hence, the required maximum number of defective articles likely to be encountered as 28. So, on comparing these two values, 27 is the maximum value. So, the number of defective articles maximum is 28. See, in the question, they are asking about maximum number of defective. So, that we are taking the highest value is 28. So here we are not using the fraction defectives. So this is NP chart. Now, now come to C chart. In this C chart, The C chart are used to maintain or monitor the number of defects per unit. This is the difference between the P and P charts and C chart. So here we are using the word defects per unit. So the number of returned meals in a restaurant, and one more example is the number of bacteria in milliliter of water. The types of units of measurement we are considering are a period of time, a surface area, a volume of liquid. So these are the examples of C chart. Defects means these are the two examples we are taken. Okay. Control chart when the standards are not specified. So when standards are not specified, in this case you are using CL. For calculation of CL is C bar, and UCL calculation we are using C bar plus 3 square root of C, and LCL is C bar minus 3 into square root of C bar. So these formulas, three formulas we are using when they are not given the standards. Next, control charts when the standards are specified. See here, the central line is at sigma, where C2 sigma, where C2 is formed out from the tables, statistical tables. Standard error sigma is sigma by square root of 2n. These are the central limits. And alternatively, you're using for LCL is B1 sigma and UCL is B2 sigma, where B1 and B2 are found out from the tables. Now we are going to see problem. The number of weekly customer complaints are monitored at a large hotel using a C chart. Complaints have been recorded over the past 20 weeks. Develop 3 sigma control limits using the following data. So, weeks, they are given week-wise number of complaints. So, this is the given data. Using this given data, the average number of complaints we calculating like this 44 by 20. So average complaints, when you're adding these all, you get 44 by total weeks is 20. So 44 by 20 means 2.2. That is C bar. And come to UCL, that is C bar plus 3 into square root of C bar, you got 6.63. And come to LCL, this is instead of plus, here you are using minus, you got a negative value, that is minus 2.25. This is the first case we are seeing this my negative value. So in this case, in this negative value we got, it is tends to 0. It will be taken as 0. If you got the negative value, this negative value we are taken to 0. So LCL value is 0. Okay. Now come to the chart, control chart for the C bar. Taking the sample points, that is weeks in the x-axis and complaints in the y-axis. First, draw the control line, that is C bar. C bar value is 2.2, and upper control line, that is 6.63, and lower control line is minus 2.25. It will tends to 0. We are taking it as 0. That is clearly x-axis. Okay, and plot the points First is 1, 3. Second point is 2, 2. First point is 1, 3. Second point is 2 for 2. And third point 3 for 3. Like this, we are plot the points. So, what is the conclusion when you are seeing the graph? All the sample points lie inside the UCL and LCL. So, since none of the points is filling out of the control limits, the process is under control. So, this is the conclusion. So, we completed P chart, NP chart, and C chart. So, difference between the charts is P chart and NP chart is mentioned in the question is defective, and come to the C chart, they were mentioned in the question is defect. This is the differences between these. So, from this, you are concluding the queuing theory. Sorry, statistical quality control. Thank you.